Hello, everyone. Good afternoon, good evening, good morning. Now, let's focus next maybe 2 hours. We are going to finish the USNCO 2026, the part one, the last 30 questions from question 31 to question 60. And in those questions, I may spend these questions, not only focus on these 30 questions. Each question, if possible, I will discuss something related. Those questions. Some questions are very good. Some is very good, okay? Now look at the first one. When you look at, so this question is about the buffer system, right? And this week it's warm up quiz, or it's about the buffer system. Okay, so you look at dihydrogen phosphate with phosphoric acid. In this system, there could be 3 different buffers, such as that's the one. The second one, right? And the next one, the last one, and each one have a different, will have a different pH. It's very practically also it's very common in the lab, especially in the biology lab. Phosphate buffer system. Now, so it's give us pKa1, pKa2, and the pKa3. The first one, we need to choose the buffer pair. So, right, buffer, we need to choose the acid and the conjugated base. Right, we choose it. How are we going to choose it? See, pH equal pKa plus log the base and the acid. Now, when we do this question, the first one, how are we going to make a buffer? Did you remember? How can you do that? The first one, you want to check the pKa close to the pH. pKa close to the pH. So in this case, because the pH equal 2.3, now you should select this buffer pair. So the buffer pair is what? It's this one. So that's why you need to find out. You choose the buffer as the base pair, okay? Right? You need to choose the buffer pair. So that's the first one you needed to do that, okay? The second one, when we calculate, in this case, they said how much must add. Could it be mass? Could it be more? So normal case, it should be mass. Why? You use balance to weigh the mass, make it a solution. We can, there's no more balance. You weigh more, you make a solution now. Right? So in this case, since that buffer pair in the solution, so they have the same value, so that we can do pKa. In this case, it should be pK1 plus log plus N base and N acid. Right? So now, since here we know what? We know what's this? We know N acid. We know that, right? So which equal 0.4000 liter. You times the molality, 0.200 mole per liter. So you get what? You get a 0.0800 mole. Did you see? So Now, so easy to do that. We know pH, we know pKa, we know the acid. Now, let me write one more time. So you get what? The pH 2.0 and 2.12 plus log and the base, which means it's a sodium hydrogen sulfate plus divide 0.0800. Now you calculate. That should equals 0.121 mole. Now, here they said, what's the mass? Most likely should be the mass equal what? Equal n times molar mass. So if you ask your mass, should it be 18.9 grams? Should it be 18 plus 18.9 grams? Not that's it. Now, when you do this question again, go back. The first one, we need to find the buffer pair. Based on what? Based on the pH. You wanted, did you remember the buffer capacity? You want the pH close to the pKa. Then you adjust the acid, the base buffer pair from 1 to 10 to 10 to 1. The highest buffer capacity in this should be 1 by 1. Now, how are we going to calculate the buffer capacity? We are going to discuss in the separate class. In the separate class, okay? Yeah, there's a couple questions for you to practice. Right, now go to next one. So what do we learn here? Remember, you first of all, against the pH, required pH 2.30. Now you should choose pKa. You choose the buffer system or buffer pair. Then you calculate the C. You can use base acid this way to do that. Okay, you got it? Very easy to do that. Now, the question can change. It's a very simple buffer system. The change now change what? The ask you calculate the mass. Now they add some water. Doesn't matter. Listen, on Wednesday, we will have a couple of questions to practice. It's a buffer, related to buffer. Couple questions. You're going to do that. Some question power you never see before. And that's the way it is. I'll go to next one. Here is a very nice question about chemical equilibrium. Now, in terms of thermodynamic, chemical equilibrium belong to the thermodynamic. In terms of thermodynamics, question could be extremely easy. That's all the time. That's all the story, not anymore. So question could be very challenging. I'm expecting next year in the future, thermodynamics, including chemical equilibrium or chemical equilibrium, will be very challenging. Look at this question. This question is hard to know, but compare previous one, little bit challenge. Now let's do that. PCl5 gas, when we heat it, will decompose. Well, everyone know that. Now in this one, you look at here, it sometimes ask you, increase the temperature, increase the pressure, add PCl5, remove Cl2. What's the shift? The same thing in this question. The only thing they use what? They said the volume, the container adjustable. Increase, decrease, the same thing. We said pressure increase, volume decrease, the same thing. But the difference is what? Now, see, what's the percentage, or not what's the percentage, look at increase the volume content by what is the factor? Question get a little bit challenge. And in this case, at the equilibrium, the temperature, certain temperature, which means T is the same. And we know that when T is the same, which tell us K is a constant. The equilibrium constant only will change when change the temperature, such as log K2, K1 minus delta HR 1 over T2 minus 1 over T1. Now here the temperature same, now temperature same, T is the same. Now basically it's what? The first one, you establish equilibrium. Now what? Now you change the volume or change the pressure. K no change, but equilibrium can shift. Equilibrium can shift. God, that's the question about. It's so cool. I like this question. I really like this question. So the first step, you are going to calculate Kp or Kc. Use what? Use K equal what? Equilibrium concentration. And PCl5. Now, basically the question said 20% decomposed. 20% is decomposed. So look at E at the equilibrium. 20% initial, you can say, now let me write a little bit more detail, okay? So initial, if we said it's 1.0 mole, here should be 0. Now E, 20%, can I say it's a 0.80 mole? Here should be 0.2, here should be 0.2. Why the change should be minus 0.2? Here is a plus 0.2, plus 0.2. And you said everything is so easy. It is. Plus Asia. If we really understand everything is easy, look you down the road, look at the question. It's so easy. It's so easy. Really look at next year if you can get a 57, 58 level. We are going to work hard. Okay, I will select lots of questions. Now let's do that because it's a molality. So you get what? You got 0.20 V, 0.20 V. What's me? V, that one is what? It's a volume. Now here it's a 0.80 V. You just do your math. You do your math. And should it be 0.050 divided V? I think that's the one. So remember, K is a constant. This one will not change. We can change the V. Then change, where is the change? I cannot see well. 50, that's it. Shift. Now, second one, we can increase the volume or we can decrease the pressure. So now I said new volume. So what? I said V prime. Now in this case, you under the new equilibrium. Now it becomes 50. Now I'm right here. So E equal what? 50%, one more, you get 0.50 mole. Now here is a 0.50 mole. And here is a 0.50 mole. Right? Now K no change, but this time K equal what? Can I say 0.25? 0.25, that's right. Divide V prime square divide 0.50 V prime. So you get what? You get 0.50 V prime. K is the same. It's 0.050 V. Do the math. V prime equal 10 volume. What's it mean? Which means you increase the volume to 10-fold. What's the factor? 10. So that where increases the percentage of a decomposition to the 50% at equilibrium. Look at class. Listen. Really want you reflect. I will send you lots of questions, very unique questions, like this type of question, but you need to reflect. If you are not reflect the question, you cannot finish. Can you finish JPH question? No way. You finish, you get a gold medal. You will not, but you reflect. Okay, now go to next one. See what's here. And this is very important. See, use what? Use degree of decomposition alpha. Very useful for Olympiad results. In the first equilibrium, in the second equilibrium, you get it. Okay, so look at the shortcut, and that's the shortcut. That's the shortcut. If you remember class, I do not know how many you remember initially. I'm not sure you remember or not. Last year, advanced class, we did a similar question. The other question is what? It's an organic compound. It's a diene. Basically, it's a diene. It's a yin or diene. It decomposes. It's a reverse Diels-Alder reaction. Similar question like this. So when I see this question, I said, my God, we did in the class. Not identical, similar. And the other question use this way. Use this way to do it, okay? Yeah, I really want the class, we are going to reflect. No way we can finish all the questions. Reflect is the key now. Go to next one. This question in the USNCO at least for 10 years. Used to be, it's what? Used to be, it's not used solid. This is the first year to use solid. Used to be is what? It is water such as now. Right? And the first one is vapor pressure. Vapor pressure, did you remember what's mean vapor pressure? As long as some liquid at that temperature and that pressure, it's a vapor pressure, it's a constant. And we can use a cylinder, we pour the cylinder, then look at what the change with the volume and the pressure. It's just like a curve like this. Now, this year, they use solid. They use solid. And heat it. And it's the same thing. When I read this question, I said, this is the exact this one. That's why again we need to reflect. Now, if you can reach a level like I'm in, and this question you will get. I do not need to read. That's the question answer. A, you check. Should it be A? There's no another way. What's the mean? In this region, it is a vapor pressure. So for the liquid, as long as some liquid, and that pressure, it is a vapor pressure. In this case, as long as some solid, that pressure should be K. That pressure should be Kp. Kp is a rate constant. In this temperature, should be equal 0.12. That's it. That's it. Now, of course, I'm going to wait to do that. I'm going to wait to do that. See, here, landing point we'll discuss in a minute. I'm going to do this question, okay? So, temperature is the same. And here it's a solid, here it's a solid. Now, equilibrium constant Kp equal what? Equal Pc CO2 equal 0.12 bar. Listen, bar is okay. It's okay. Now, remember, I'm going to repeat. As long as the solid calcium carbonate are present, as long as this both present and the lead pressure will not change. So that's why. See, this one. Now, there's no other one. There's no other one. See, here it's not, doesn't make sense. Here doesn't make sense. And here doesn't make sense too. Now, could it be? On this, as long as the bubbles will not, until this point, this one will not exist. Now you got, you only have this one, which based on what? PV equal nRT. When your volume increase, and then P increase is not linearly, it's this way. PV equal nRT. What's the relationship? See? Cut it class. Now let's do that, okay? Now, see, some question, even you do not need to do that. That's the one. You do not need to spend the time to do that. So now, next one, I wanted to what? I wanted to see more. How many? You have 1 gram. You divide the molar mass. So you should equal 0.0036 in the figure, okay? More. Right? Now, if all decomposed, all of calcium carbonate decomposes, so you get what? You get NCO2, and the lead is MAX, maximum. That should be equal 0.00999 more. 1-to-1 ratio. Now, so we get based on PV equal nRT. So we can calculate the V equal what? I'm not going to do the math. You should get 8.3 liter. Right? So, and the latter one, this is the key point, the volume. Now, the first one, if we less this one, what's the mean? And in this case, only partial decomposed. Only partial decomposed. We have what? In the system, you have this one, you have this one, you have this one under the equilibrium, which means P equal what? That's carbon dioxide. It's a 0.12 bar. Never change. Next one, if V greater 8.3 liter, what's the mean? Which means this one is gone. Then you only look at the carbon dioxide and the P with B. That relationship is what? It's a PV equals C. That's a relationship, okay? Right? So should be this one. This is really cool, my friend. This is really cool. Like this question. Right, now let's move next one. See, look at the Olympiad learning. See, that in the Olympiad exam all the time, please remember that curve. Right, by the way, each year they use so many curves. Right, so this one learning is heterogeneous equilibrium with a solid. Pure solid is not. Then it's this one. See, now you just look at what only if enough calcium carbonate remain the system, and in that one is what? It's only equal this one. If all gone, then use this relationship to find the pressure with the volume. Now go to next one. What's this? I like this question. This question is just the regular the titration. Right? The titration is what? It's a buffer system. It's a buffer system. Look at So what do we have? And this one, you have a diprotic acid. And what's this? That one still has one proton. Did you see? Now look at the curve. Look at the curve. And here it's about 2 mil. 2 mil. Let's put that this way. What's this? And that is 8 mil. You know what? And it's a choice. Do not need to do that. Should it be A? Now let's do that. What happened? What happened? And the reaction is what? Let me write it here. Okay. So reaction should be diprotic acid. You react with a base. Net ionic equation, please. Right. Now the next step is what? Right. Now this one in here, can I say the first equivalent point? At the first equivalent point, only diprotic acid become the first proton. It's neutralized. Right now, the formed with original, then go to second equivalent point. So in this one, it's a 2.0. Now, what's the molality here? Basically, it's what? It's a 2.0 millimole. Now you add here, see, here it's a 2.0 millimole. Now here it's what? Here it is 8. Right? That one is 8. So what happened? What happened? So now in the second equivalent point, you also 2 point plus original one is N. Right? So what happened? Should it be 2 times 2 millimole plus N original one equal what? Equal 8 millimole. So you calculate that one should be 4 millimole. The ratio should what? That should be 1 to 2. This it should be 2. This should be 1. All question can change. That's the way to do that. Okay. Now, what's the Olympiad learning? Again, I want you reflect. Let me tell you myself. Every time when I write the question, after I did the work, I reflect. Then I adjusted the reaction, the question. So that's the one. Now, so you first equivalent point beginning here. Now, the second equivalent is what? See? Then you get what? You get overall calculation. Right? Now go to next one. This one, it is related to equilibrium, okay? That equilibrium. Now, in the equilibrium, there's so many equilibria, but they do have a relationship. So always in this case, that always true. In this case, always true. In other words, there's only one molarity concentration from 2. That's the same. Now, that one is different based on what? Based on KHP, KSP. Now, look at this question. So the question, if we add these 2, we add, now I want, here is a smaller KSP, This one is smaller than this one. So what happens is, and basically you will have a replacement. If we reverse this one, it's equation 1, and here is equation 2. We are going to reverse equation 2, then add the equation, becomes 3. Then you add it, you get what? Equilibrium, okay? Right? This is very interesting, a very interesting question. So this one will dissociate. And you dissociate, you go what? You dissociate, let me write it here. Now, in the solution here, Br minus, and that one, so that equilibrium shifts to right. If you have not more enough this one, and that should be dissolved. That should be dissolved, okay? Now, let's look at how I'm going to do it. The question said, you have this one, you have this one. What's the concentration silver? What's the concentration silver? You can use this equation. You can use this equation. Right? Now, why? You look at, you want to calculate silver, you got what? You can use KSP with Cl minus. You can use KSP, what's this? As a silver chloride and a silver bromide. Right? You want to calculate this, you need, if you know this one, here it's also the same. You find this relationship too. So in order to find the silver ion, you need to find what's the concentration in this one. Or the question also asks you, what's the concentration this one? Right? So many questions can ask you. The same question can change it. Now let's do that. Let's do that. Remember. So we need to find the silver ion. Either we need to find the concentration bromide or chloride. It doesn't matter which one. Now, let's use this way. I'm going to use KSP Now, in order to calculate this one, I wanted to calculate this one. So I want to calculate the Br minus equal what? Now, how can I do that? From this equilibrium, we can calculate K. So K equal what? Equal KSP. And the KSP. How did you get it? So from here, see, that's equal, right? If you got it? So if you cannot see it, you write the KSP here. You write it, then silver ion cancel it, and chloride, use this equation. Use this equation to do that. Use this one. Now, you solve this two, you get a KSP. That's a way to do that, okay? So if you calculate, and that equals 3.67 times 2. Now, original is a BR. Let me write it here. Original one. That equal what? Equal 0.100 m. Now I say EQX. So in this case, based on stoichiometry, chloride should be 0.100 minus X. Now you put a K equal what? Equals, where is the K? Cl minus Br minus. It's a 0.01 minus X. You divide X equal what? Equal 367. So you calculate X. You calculate X. And that X equal what? Equal Br minus equal what? 2.7. 2 times minus 4. As we know that, right here, KSP, zero ion, Br minus. We know this one. Now we know this one. Then you calculate, which equal 1.8 times minus 9 molality. Okay, Jimmy. And also, if I ask you calculate what's this concentration, then you should do that. You use what? KSP with CR, right? And that is here. That's one. Or I can ask you calculate, expand. What's the mass of the second one? What's the mass of? So many ways we can write, right? Okay, so see, what's the Olympiad learning? Remember, in this case, there's so many equilibria and all related. There's only one concentration, which is a zero ion. That concentration is the same, not a different equilibria have a different concentration. No. We will discuss more when we discuss the chemical equilibria. Let's go to next question. That's the next question. See, this question is the same. This question, right? This is a very good question. Not hard at all. This question, every year we discuss, use what? Hydrogen sulfide to separate metallic ions. Then I'm going to identify. Although it's very toxic, smells so bad. Right? As we know that in the aqueous solution, that the saturated should be equal 0.1 m. That you should remember. Here also tell you, this question is classical like a Chinese question. Because when I'm in the college, we do all the time. Okay, and also what's mean? You precipitate. That's called the selective precipitation. Did you remember we did last year? There are two ways to separate ions. So one way called precipitation selectivity, selective precipitation. That's one. Second way is what? Electrolysis precipitation. Two way. Now use this one. Very simple. Ratio. Since use ratio. Do we have ratio? Yeah, that's the ratio. See, between this one ratio. Now let's look at. Question said you want a CD. That one you want to come out 99.9%. So in this one, you want to see CD2 plus, and the left should be equal, smaller equal what? Original concentration is 0.1, and the left is what? It's 0.001. Now you calculate the concentration. So you get 0.0 times minus 4. Not more than this one in the solution. Not more than, okay? Not more than in the solution, okay? Right? Now how can you do that? So you look at, you find C, because KSP equal what? Equal CD2 plus 2L minus. You need to find the concentration that one. This one should be not more than, so in other words, what's this? Basically, it's what? It's this one. It's a QSP, right? So basically, it's a QSP equal KSP. So that you want this one great. Great equal what? Great equal KSP. Or not KSP, the great. See, because you want this one is less than this one should be great, so that QSP equal KSP. Now, how can you do that? And it's a way to do that is what? KSP is 1.0 times minus 27. Now, that's the one. It's 1.0 times this one. So you get what? You get 1.0 times minus 3 minus 23. What's the mean? In order, this one is less this amount. The sulfide should be greater this one. Now, how can you do that? And you know that AQ. Now, in the aqueous solution, the equilibrium is not like this, okay? But for the calculation purpose, we can. So which equal what? Ka1, Ka2. Right. So in this case, do we know this one? Ka, oh, you have a Ka1 and a Ka2. So you have this one. Now you know this one. And you know this one, you calculate the pH. You calculate the hydronium, that should be less equal 9.4 times minus 3. So you calculate the pH. pH is minus log, should be greater equal 2.03. 2.03. Which choice I not very likely should be B, right? Very likely because 2.0, 2.03. Now go to next one. Next one is what? 2. Pl plus. You want this one in solution. So in other words, it's the QSP. And that should be equal KSP. See, that should be equal KSP TL2S. Put it with me? Right? And it's the same way. The same way to do that before that equal, what do we have? 0.10. So that, remember, should it be small, then you calculate this one. Should it be small, then what? Then KSP with equal what? Equal 6.0 times minus 20. You understand? That's in it before. Now, the same way, use what? The same way, use this one. And plus square equal what? Equal Ka1, Ka2. In this equation, what do we have? We have this one, we have this one, we have this one. Then you calculate. That should be great. When this is more acidic, of course, that should be less, right? Got it? So you get what? You got 1.2 times minus 4. I think our calculation is right. Then the pH should be less 3.91. The choice, I think, is this one. Right. This question actually we did in the class. Okay. Now listen, if you do not believe me, look at your class notes last year. Much, much harder than this one. Very similar. Very similar. Okay. See, here is the key. In terms hydrogen sulfide, that's the key. When as increase, that one increase, this pH increase, and that one will increase. Now, this one also is important. Okay. Very nice question. Okay, go to next one. Yeah. Now this one, of course, this question is so easy. The first one you need to write, see the disproportionation in the basic condition. You get the NO2 minus. Let's do the balance. Plus 2, plus 1. And here it's plus 3, right? See, nitrogen from plus 2 to plus 1, gain 1 electron. So you have 2, you gain 2 electrons. Nitrogen plus 2 to plus 3, you lose 1 electron. So LCM should be plus minus 2 electron. 2 divided 2 is 1. 2 divided 1 is 2. So here should be 3. It's right? Hold on. Or 4, because it's 2 here. Now you balance what? You balance charge 2 here. Then you balance what? You balance hydrogen 2. You balance 2. Balance hydrogen with water. Now you balanced. So the choice what's this one should be 4. Now, by the way, I'm going to teach you how to balance. Very simple. Balance charge. Balance electron. First step, LCM. Balance charge depends the reaction media. You add H plus or OH minus. Last one, you balance water. You take it probably 30 seconds to do that. Okay. Now we are not going to go to that one. Okay. Now go to next one. Go to next one, 38. So you are going to calculate this one. And then this reaction, this question is related to what? This is 38. 38 and 40. Most is related to Lemma diagram. Lemma diagram with the delta G. With the delta G. Okay. So here's the Lemma diagram. Okay. Now delta G is the free energy. Why related to delta G? Because the reduction potential, it is an intensive property. You cannot add minus. You have to convert delta G equal minus NF epsilon. Number 1, that's an extensive property. Number 2 is a state function. Right? So in this one, how are we going to do that? So first one, we need to write a half reaction, right? Half reaction from here to here. From here to here is what? See? MN4 minus MN4 minus, or I write this one, okay? I write this one. Because see, let's look at it here. Look at what I'm going to find. We need to find this one. That half reaction is what? Now, let me do this one first, okay? That one, it is MnO4, 2 minus, get MnO2. This one in the basic condition, plus 6 plus 4, you gain 2 electrons. And then you balance what? Then we balance electron balance, then balance charge. 2 minus, 2 minus, you get the 4 OH minus. Then balance hydrogen should be 2 water. So that one we are done. Now that we need to find out. Okay, that one need to find out. Now in order to find this one, we need to find, you have this one and this one, right? So that I'm going to write which one first. I'm going to write this one first. MnO4 minus MnO4 2 minus, which means you gain 1 electron. So epsilon equal 0.534 delta G equal minus NF epsilon. Now go to this one from here to here. So that should be MnO4 minus 2 MnO4 2. Right? Now you get plus 7 to plus 4, you gain 3 electrons. Right? Now I'm going to balance charge. Charge should be 4 OH minus. Then I balance hydrogen, and that should be 2 half reaction. Right? So what's this? And that one equal 0.595. You get a delta G. If this is 1, here it's a 2. You get a minus NF epsilon. So what do we want to find? We want to find this one. Now we look at this reaction, okay? We look at this reaction. So you want to keep this one, oh, you need to reverse this one. You reverse it, and I'm going to reverse it, see? MnO4, 2 minus, MnO4 minus. Now it's what? You reverse it, you change the sign. Okay, right? So then you add, cancel it, you get a 2 electron. Cancel this one, plus 2. Then you what? Water. You cancel this 2. Where's water? No, this no. This 2 water. This 2 water. Right? Then you get what? Then you get MnO2. You get a 4 OH minus. Now you want to calculate this one. So how are you going to calculate? This one, the delta G1. Now that one is a delta G2 equal what? Equal minus NF epsilon. If this one is a 1 and this one is a 2, now delta G3 equal what? Equal delta G1, delta G2. Now, right? So you calculate this one is what? Minus 2F epsilon. Now, G1 is 1 minus 1F 0.534. Then you plus what? Minus, here is minus, what's the electron? Electron should be this one. Hold on. 3. That electron should be 3 minus 3. Then it's what? F. Then it's a 0.59. So in this one, you cancel this one. Then you calculate that one. You calculate. When you calculate, I calculate it for you, okay? I calculate this one for you. And that equal 0.621 volt. That's a 0.4. You see, it's typical. That's my diagram, typical, okay? Now go to 39. 39. Now in terms of Olympiad learning, you are not going to remember, we cannot get average reduction potential, no. Because that is an intensive property, you cannot do that, okay? You have to use delta G, because delta G is an extensive property, also it is a state function, right? Overall, that my diagram, if you want to remember, that's the way to calculate. That's the way to do it, okay? See, this one. In the chemistry all the time, such as you use to see, like you have a 2 container with a gas law, right? Now see, the same way. This is the same way to do that. This is the weighted electron method. It's most fast way to calculate. Use this way, or use this one. So overall electron times reduction potential, electron reduction potential, and that's called weighted electron method. Weighted electron method. You are not going to do this way. Okay, you are not going to do this way. You have to times electron. Okay, right now go to next one. This one is also it's electrochemistry. It's very straightforward. And when you look at, that's the cell notation. Anode, salt bridge, and what's this? That's a cathode. Anode always its oxidation. Cathode always reduction. And the initial is 1 molarity, which means we can use standard reduction potential. Right? You got it? And this question related to what? See, when I see the ammonia, when I see the ammonia, when I see the ammonia, it tells us, and that probably will relate to Kf in the electrochemistry. Kf in the electrochemistry, okay? Now let's do that. Let's do one by one, okay? Right. So the first one, let's write cell reaction. Cell reaction, you write anode oxidation. Then you write the cathode. Cathode is a reduction. So you have 3 electrons. So you got which is a single replacement. Single replacement. Now, what are you going to do? You said change something, see the cell potential, change something, cell potential increase, which means reaction is not under standard condition. If under the standard condition, and that cell potential will never change. Why? And right minus left. If under the standard condition, and the cell potential will never change because it's constant. So that in this case, what are you going to do? You need to use Lerner's equation, which is minus 0.0592 or 16. How many electrons? 3 log Q. Oh, this should be natural log. Now Q is a reaction quotient. It's what? It is a Cr3 plus C over Q. Initial, it's 1 molarity. You should read it here. Right? Now the question said, you want this one to decrease. So you want this one should be positive. Increase, right? Increase because initial equal 1. When are going to positive? Now you look at, so here's no change. Everything here, no change. You basically look at this one. Only when we bubble the ammonia to the cell half reaction, what will happen? Initially, you form precipitate. Now, then you dissolve, forming plus. you form complex ion so that free ion will decrease. The ammonia form complex ion with a civil ion. So in this case, that one dramatically decrease, right? So that you decrease this one and Q is increase much bigger. You make that one decrease. You got it. This question, where again, right? This is a classical. It's a classical question. Complex ion with Nernst equation. Basically, it's a Kf with electrochemistry. When you add this one, you form complex ion. Right? You form complex ion, okay? And the rest one, no, doesn't make sense. See, the stronger complexing agent, lower metallic ion concentration, you change the cell reduction potential and also the cell potential. Right? Rest it doesn't make sense. Okay, right? You got it. So the second key point is what? Surface area will not affect this. You do not get confused. Okay, do not get confused thermodynamic with the cell potential. Right? Do not get confused chemical kinetic current and reaction rate. Change the size could change the current, but will not change equilibrium voltage. Got it. Okay, very nice. Oh, we need to speed up a little bit. See, look at it. It's cool. Shortcut. I try. Now, normally I'm not going to say shortcut, but the more we practice, we do a lot of practice, then we do shortcut, save time. See, increase this one, increase this one, it's this one. Now, on that side, you decrease this one and let up. You increase this one, let up. Right? Cool. It's a cool question can change again. I want you just reflect. Okay, this direction is the same. 40 and 38 is identical. It is identical. Now, how is it identical? Let me show you. So you want to find the KSP. The KSP is this one. See, that's the KSP. See, that's the KSP reaction. Of course, we need to put the states. We need to put the states. Then it's what? KSP equal what? Equal PB2 plus SO4, right? You do this one. Now, in order to find the KSP, you need to find the concentration this one. You need to find the concentration this one. Or you find the relationship. Okay, that's the one. Now, how can you do that? How are you going to do that? Now, no, you cannot do that one, but we can relate to what? You can relate the delta G equal minus NF epsilon. And that relate what? Delta G equal minus RT log KSP. So basically you need to find it what? KSP delta G reduction potential, standard reduction potential this one. The question changed. Standard reduction potential. Now, how I can do that? Now look at this one. I'm going to see, look at this one. Okay. Can I PB? You got 2 plus 2 electron. Now it becomes plus 0.126. Now this one you keep the same. 2 electron. You get the PB that, and that is minus 359 volt. Then you add, cancel it. You get the PbSO4 equilibrium PbS2 SO4. Save time. I did not put the states. Okay, right? I should have put the states. Okay, now what's this? And that is a KSP. Now I'm going to write a different place. Okay, that should be KSP SO4 2 minus. Now what here? You just need to find the delta G minus NF epsilon minus RT log KSP. Now how I can do that? So if delta G1, delta G2, delta G3, delta G3 equal delta G1 standard plus delta G2. Did you see? Now use what? Use this equation. Then you calculate. Okay, now I'm not going to do that because we have to finish by 8:30. Okay. Yeah, we need to finish by 8:30. Okay. Now you can find the KSP. Now when you calculate, your KSP should equal 1.34 times minus 8. Now the question can ask you many questions. What's the question ask? Let's go back. I know that. That's the easy one. Okay. So in order to calculate concentration, so that or SO4, you get what? You get a KSP square root. The KSP square root. Okay. Now I calculate for you. That I did 1.16 times minus 4. This 40 and 38 is a very common one. That question is very common. Now go to next one. Go to next one. Here, look at class. So I reflect myself. The common Olympiad trait. Both is a reduction. You cannot simply subtract. Instead, you reverse one, you add to another one, then you add delta G. Then, so potential cannot add delta G. Yes, as we said, right? Typical problem in the USNCO is what? Or KSP with KF, equilibrium constant, and related electrochemical data. This is a very, very, very common question in the US national, all countries, including ICHO. You have to know this one very well, very well. Now go to next one. Go to next one. I like this year, the electrochemistry, the design. This one also is very good. Very good. Look at the question. STP 22.4. So we can simply find more of hydrogen is dry. If not dry, you need to minus the vapor pressure, which is third not of partial pressure. Now, so can make it more complicated. Now, they said you have 1.5 grams metal in deposit in the cathode. Oh, in this case, basically what? That reaction is related to electrolysis. Electrolysis, let's look at STP. So we can calculate N oxygen equal what? Equal 0.256 liter, 22.4 liter more. That's why I want you to treat it as a constant. You get 1.18 times minus 2 mole. Now, look at the half reaction, and that one should be in anode. Should be in anode. Anode. You lose electron, you get oxygen. How many? You should lose 4 electrons. So now balance charge should be 4 plus. And here should be 2. 4 electrons. 4 electrons. So we can calculate N electron is what? That should be 1.18 times 4 or times, today is a crazy computer, very slow. I'm going to slow down too. Computer reminded me, slow, JPH, please slow down. It's times 10 minus 2 times 4. So you should get 7,473 times minus 2 mole. That's the mole. Now, in order to determine which metals, we need to find the molar mass. We need to find the molar mass. And electron conservation during the electrolysis. In the anode, you lose the electron equal cathode. You gain electrons such as M plus, you gain N, M. So lose electron, gain electron should be same, so that what I can do, I look at 1.50 grams. I divide 4.73 times minus 2. I find what? I find 31.7 gram per mole electron. Now, if plus 1, here there is no plus 1, the molar mass should be 31.4. If the charge is plus 1, you should get 31.7 gram per mole. There is no. Now, if plus 2, you times 2, you should get 70.7, 6.3 per gram is 2. If plus 3, so the answer should be this. The answer should be this. Okay, got it. Very nice, very nice. It's the same question. Electrolysis, what? But the problem is changed. The problem changed, okay? Now go to next one. See, here, what's the Olympiad learning? Olympiad learning is that, see, safer is the method equal what? The equivalent mass equal what? Molar mass divided number of more electrons. Okay, what else? Problem have enough. This one is good. Oh, haha. Here, everyone should have a good habit to calculate, compare with order choice, choose best match. Only then consider chemical that one. Okay. Yeah. Okay, let's move next one. This question, we are going to spend the time discuss. Okay. Not here. I will spend at least 2 hours to teach you. This is the first type of question. And next year may happen again. The question, look at, here is the pH. Here is cell potential or reduction potential. You need to look at the 3 parts. You look at this one. You need to look at this one. You need to look at this one. Okay. What's mean? You need how to read it. The first one, let's look at number 1. Vertical boundary. Vertical boundary. And the vertical line indicate equilibrium. Vertical line is this one. And that what vertical line indicate at equilibrium does not involve electron. Does not depends on the potential. Can you see? Can you see this line? Not involve electron, not involve potential. Okay, that's the one. Okay, you write it yourself. Right. What's the mean? Which means it's a simple precipitation. Precipitation equilibrium. In this case, it's what? Plus water and 2 plus. Now, look at the next one. Horizontal line. Horizontal line. And that one is what? See, is this one. That one is what? That one equilibrium depends on the potential. The potential, not the pH. Can you see? So this line, horizontal line, indicates an equilibrium that depends on potential. See, potential here is 1.2, here is this one, here is 0.8. Not depends on the pH, pH equal 2, no change. So which means the reaction have to, such as gain electron, mercury. No hydronium, no OH minus involved. No H plus or OS minus includes. Okay, now look at here. The third one and that one, look at the slope line. Sloped line. Look at this one. And that one involve both electron and proton. See, pH change, so potential, the potential change, so involve both proton and the electron, such as see. Involve both, right? And that's why, so it's why pH dependent. pH dependent, okay? Right, now that's the first one. You need to read the diagram. Now go to next one. Now look at which species fit between this one, which fit this one. Which one fit? And that one is one, you know this one, right? You form metallic bond. You form metallic bond. And when equilibrium 2 plus 2 electron, you get here. Right. And 2 plus both are pH dependent. So what's the X? This is very nice question, okay? Right, remember, we are going to do this question. I promise you, I'm going to very detail, and also this is classical. You look at Advanced Inorganic Chemistry book. The first example is this one. The second example is related to bromine. We are going to, classical one, we are going to discuss. Okay, when I see this question, I said, my God, this is a hard question. This is the hard one. Basically, it's what? It's a poor blocks diagram. You have many diagrams. Right? We then what? Letma diagram. Later on, you have 3. This one normally we did not discuss. In the actual level, we discuss. In the advanced level, we not. But it's very good to look at the vertical line, look at the vertical line, horizontal line, and this sloped line. You get it. And the rest doesn't make sense. Again, I'm not going to worry about this one. Why? I'm going to spend hours discuss it. Whole class, you will get it right. Next year may have a similar question. Right, I go for next one. See, look at here. I'm summary. Okay, how read diagram quickly. Memory, this is 3 boundary memory. Okay, Victor, vertical line and as the base precipitation equilibrium, no electron. What horizontal line, redox equilibrium, electron. The slipped line is redox is at the base. So for USNCO and IGEL, you should be able to identify unknown species without any calculation. Do not need to calculation class. Do not need to do calculation. Okay. Yeah. So see, this question is very unique, often tested in the Olympiad level in the inorganic chemistry. Very common. Okay. Very common, right? Okay. Now this is easy. Now that if we can finish another hour, very great. Okay. Very great. Okay. Right. Okay. So this one should be easy, right? And the answer should be this one. Why? As we said, ionization age, you pay attention to 2A, 5A, 8A, right? So the first one, the trend should be what? That trend should be this one, this one. This one is this one. That's the trend. The second one, we said, do you remember pi C, pi E, right? And always the case, 5A, 2A. So now this one is greater than this one. It's nothing to need to go that, okay? See, did you remember most important first ionization age exception? It's number one is what? That's the 2A. That's a 2A. Number two is what? That's the 5A, right? Did you see? What was we said the case, right? So that's the one. Now the second, the shortcut is what? 2, 3. You remember this one, this one, this one is this one. And often, almost all multiple choice has this question. Almost one. Okay, go to next one. This one question, if you read carefully enough in my notes, you should get it right. That should be this one. So of course, we can do that. Why is this one? Did you remember in the hydrogen emission spectrum in the visible light, you have a 4 line. 4 line. 6 to 2, 410. 6 to 2, 410. 5 to 2, 334. 4 to 2, 486. 3 to 2, that is very narrow. So wavelength longer. So that's why you look at. Now, somebody we can calculate, okay? We can calculate. I give you some common multiple tricky. Yeah, tricky, we can do that. Now here it says way we can check it. We can check it, right? We can use what? First the topic, we spend a lot of time. It's 1 over lambda equal RH 1 over 2 squared minus 1 over n squared. N equals 3, 4, 5, 6. And RH equal what? 109, 677. You just do that. You just quick check it. Now, there's one way to check it. There's one way to check it, right? Let me show you. If you said 549, 545 is right. Go back. Or 545. If this one you said it is a Borman line, what will happen? We use this equation. We use this one. What do you have? See, it's 1 over lambda. 1 over 656. The question tell you that's the one. right? That one tell you it's the 1. And equal what? Use this equation. It's 1/4 minus 1n squared. Now in here it's what? 1/4 minus 1/9. So you only have 1 known, and if we do the math, very simple, you get a 3.56. 3.56, and that is not integer. That is not integer. You have to integer. So that's why it's not. It's not, okay? That's why it's not. Got it? So those questions is a good question. And by the way, this question also reminded us. I give you the notes. Everything in the notes. When you read it, go through it. I'm not going to ask you memorize, but if you remember, will be great. I'll go to the next one. This question is tricky. This question is very tricky, okay? Why is it tricky? This question, some wording is not good. The wording is not very good. Why? Let me tell you, okay? So in here, we get CR, which is a 2080 degree. And next one is MO, which is a 2896 degree. Next one is a W. W is what? W basically is a period 6, 395. And all valence electron is the same. You have 6 valence electrons. Six valence electrons. And the boiling point increase. What's the reason? The reason is that, and we look at what? We look at metallic bond strength. We look at metallic bond strength. And the metallic bond, of course, it's a positive charge, the cation, right? It's a cation. And with delocalized electron, right? Now, when that interaction is strong, the stronger this electrostatic attraction, the more energy required to melt metal, okay? And the choice is what? It's this one. It's B. Why? Why? Metallic bonding becomes stronger from Cr to Mo to W because the d orbital give increased effective extended metal-metal bonding, especially for this one. Okay? Remember the difference we discuss all the time, 4D and 5D. 4D, 5D normally spatially extend than 3D. So that 4D, 5D allowing stronger overlap between neighboring atoms. That's the first reason. The second one, why this bond is strong? The second one, for this one, W, of course, remember, W, you have what? You have 6s, you have a 5d orbital. And that also related what? Relativistic effect. We discussed in the class, but in this question, it's very tricky. We are not going to overuse this one. We are not going to overuse. Why? Because relativistic effect, this one, no. So do not have it. That's the wording problem. Okay, that's the wording problem. Now, last one, the packing, that's not make sense. That is a false. Why? Because all this one is a BCC. Or it's a BCC. Okay. Or it's a BCC. Look at it. The 3 metals crystal as a BCC structure. That starts to make sense. Now you know the fact. So that's the one. So I can expand this one. I can at least for half hour, to be honest. But let's move on. We have a summary to do. Okay. Now go to next one. Go to this one. This one you look at the key point is what? Let me tell you the answer. The answer is this one. The key for this question is what? It's low energy exciting state. Not lowest excited electron configuration. That's the key point. Repeat. The key for this question asks for the lowest energy excited state, not the lowest excited electron configuration. The lowest energy excited is what? You keep the same configuration. You keep same configuration, which is 1s2, 2s2, 2p2. But you change the spin. You change the spin arrangement so that you give high energy singulated state. That's the one. Repeat. Repeat. This is excited configuration. Okay. Right. So remember, I'm going to repeat. It's lower is the energy excited state, not lower is the excited electron configuration. The lowest excited state keep the same configuration, but change the spin arrangement. USNCO National ICO. And that one allow advanced lowest size state over another term. It's the same configuration, not the promoting electron configuration. This is a classical example. Look at USNCO. If we really get the insight, it's always a classic, always a classic. Okay, now next one. Look at this question. This is the first time. Before we learn what? Affinity gain electron. Here also is gain electron, but it's not affinity. It's not affinity. It's what? It is compound. And that relates to 14. What means 14? NS2, NP2. And the NS2 is laser pair effect. It's laser pair effect, okay? Right? 14 is laser pair effect, okay? Now in this one, you look at the reaction. Look at the reaction. Let me write it here. You get 4 electrons. You get the S. You get the 2. Now we have reduction potential. And then we know that, what's this? SiO2. That is crystalline, right? Extremely, or I can say extraordinarily stable. You know that. This was what? It is sp3 hybridization. Crystalline structure. It's a network covalent. Hard to reduce than carbon dioxide. So reduction potential should be what? Should be more negative, not positive. So first one is wrong. The second one is right. Why? Because see, PbO2 that more easily to reduced. Right? It's more easy to reduce. Why? Why we learn that? Laser pair effect, inert pair effect, which become increasingly important down the group 14, 13 to 15, group 14, 15, 14, 15, 13, 15, 13, 14, 15. You have 6 pairs. You have 6 pairs. And indeed, this one is a very strong oxidizing agent, very stronger, okay? Very, very stronger. So, and this one is right. The choice should be only this one. And remember, so when you see this one, when I saw this compound, I remember it's a very strong oxidizing agent. By the way, the fourth decoding class we're going to discuss. The second one, have you heard the lead battery? Did you heard the battery, car battery? No, not the Elon Musk, okay? The car battery, okay? Did you use what? You coating with lead. That one in anode. Now in the cathode, you coating with this one. This is the reason. This is the reason. Why? Because very high reduction potential. They use the lead acid car battery. Why? Because it is a very strong oxidizing agent. Remember, huh? Very strong oxidizing agent. This is the reason. They can write another question. Okay, so we done this one. Now go to next one. This one is very interesting. This one is very interesting. Okay, now before do that, I want to do some review. Okay, Olympiad learning is what? In terms when you will have a beta decay, neutron rich, beta decay, right? Positron decay or electron capture, you will proton rich. Now you have alpha decay when nuclei over 84. You have gamma emission. Basically, it's excited nuclear. Excited nuclear. In that case, you will have a gamma emission. Now, this one so far, there's no exam. It's on the way, I can tell you, such as, or it's a classical one. 6028, you put a star, and that's called excited nuclei. So we have a gamma based release energy. You get what? Nickel. You get a normal 28. Now, in this case, everyone, this at least is second time take exam. That's the second time we take exam. This question, you know that, right? There's one question related to what? Chemical kinetic, which I forgot part 2. Part 2 or part 1. You know what? TC have no stable isotopics. Every isotopic of TC is radioactive. Everyone should know that this is a famous chemistry factor. And in this case, the G equals 43, right? And specifically fell into the gap, and that is no any stable species. And we compare called value over stability. I hope everyone we did not discuss so far, we will value of stability. So in that one, like MO, so that's Z42, like IU, Z44. So you look at the neutron to proton should be 1.2 to 1.3, and that is stable. Now look at this one, should be 49 equal 1.14. Also, that is relatively low. So which tell us is what? Move please. It tell us it is a proton rich. So we have positron emission. So we have a positron emission. This is really cool class. This one, I'm going to planning to do more. We do more, okay? I'll go to this one. This is easy. You draw the Lewis structure. That's a linear, okay? Now here, remember, you have 7. Seven minus 4. That one should be what? Should be bent. But this bound angle is less 109.5. Okay. Yeah, I can expand. Now let's move on. So here, look at the other electron. Let's okay. See, a pair this one. They also need an orbital, right? Not the orbital. Now that many students see 2 electron touch center a linear field. This is not linear, not linear, not linear. You remember within the class we discussed electron domain, geometry, and molecular domain. Did you remember? So look at here. This is a linear. This is a bent. We do not go too deep. This is so easy. Now here it's easy too. Right? You draw the Lewis structure. Minus. You have to be zero. You have to be zero. Or and here it's minus 1/2. Here it's minus 1/2. Okay, right. So the answer, I think this one should be 0. That should be 0. Oh, that's right. That's right. Oh, look at Olympiad learning. Okay, formal charging. We did so long. Okay, now what's this? Bound order. That's a bound order. Today, someone sent me email. Do I have to learn the MO? I said, why not? You have to, of course, you have to learn MO. So ask this question: 2 minus. Without MO, can you help me solve it? I said, no, I cannot do that. I cannot do that. So we are going to, Wednesday, we are going to learn MO. And this one basically is what? That we have a mixing. And that MO orbital, just like isoelectronic, like nitrogen, we're going to discuss it. And both is a triple bond. I want to save time. There's a common question I want to discuss. Okay. Now, what's this pi bond? That's easy. Carbon, hydrogen. Did you remember in the class? That's the topic. This is 100% there's a question. So you can ask what's the relationship? This is conjugated or not? It's not conjugated. We discussed. So how many? And that one should be 6 sigma bond. And 2 pi. We discussed so many. Now I want to spend some time in 53. Okay, I want to have some time here. And the choice is this one. Why? Why is this one? This is great. It's beautiful chemistry. I think when we shape part, we briefly discuss this one. The connection is this one. F, S, S, 3. So this one you have 2 lone pair. This one just like SF4. SF4, okay. That's called what? Should it be SF4? Should it be seesaw? Should it be seesaw, right? And this one should be bent. You got it? So that basically is what here is related to AX4E. That one should be trigonal bipyramidal electron domain. We'll discuss this one. What's this? And that is radical. It's a radical? Yeah, it is a radical. See, 1, 2, 3, 4, 5, 6. Yeah, it is a radical. That's not stable. Now, what's this? That is That one, it is the bridge. F as a bridge is okay. To do have a bridge, F is well, see such as AS5, SH5. We did the homework last year. Those is a very strong Lewis acid. Now they do have a bridge. That bridge is what? It is F, ASF, F. That's the bridge. Okay. So you will form what? You basically form this an ion, right? I hope you still remember. And 11 minus S2, F11 minus. So do form bridge. F minus a bridge. However, those two compounds, it is a very stronger Lewis acid. That F minus, it is a base donor. However, in the sulfur, they are not electron deficient. No, it's not. You look at. So that they will not form bridge. And it's this one. Now, what's the shape of this one? And that shape basically is what? This one just like seesaw. So you draw the here, you have a long pair here. And this one just like a band. Did you see? Just like a band. Okay? Right? Now, if any evident, you say that, yes, I do have evident. I'm not joke. I read the original paper about this compound. They use fluorine NMR. Can anyone tell me how many signal? How many? That is a 4 signal. One here, one here, one here, one here. One fluorine in the terminal sulfur in this one. Why is this one? That's called the equatorial hypervalent sulfur. Why is this one? And that's called axial. Why is this one? And you said, why this is not the same? No. So two reasons. Reason number one, so this bond cannot rotate. Sulfur bond, you cannot rotate or sulfur. Why? Because you have 2 electrons here, you have 2 electrons here. That's the one. Second one, the do form, we know sulfur, this bond, it's from single bond. However, and in that case, they do have some degree, overlap. Some degree overlap. How are we going to overlap? So the overlap is that, so you have lone pair, and that is a HOMO. Now for this one, you have a LUMO. So some degree, plus you have a lone pair where it will form the berry rotate. So in other words, so this one, this two is different. You can see the animal proton. You can see the 2 signal. Okay, I'm going to repeat. This is a very good question. Can be in part 2. Sulfur bond cannot rotate. Because rotation is strongly hindered by hypervalent bonding and lone pair electron. That's number 1. Number 2, the molecule has a preferred conformation, the conformation with significant rotational berries, so that the NMR time scale, the fluorines remaining is in not equivalent. So you have a 4. You have 4. This one. This is a very nice one. This is a very hard question, okay? We may discuss before. Okay. Now this is easy. This one reminded me what? Reminded me 18 electron load. 18. We will have one class related to 18 electron load. W is what? Xenon 6s2, 4s14, 5d4. So that it's 2 plus 4, 6 valence here, plus here 2 times 6, 18 electron. So that is a tetrahedron. Now this one is a square planet. That's basically is what? It's AX4E2. Right? Now let's move on. Now we still have finish. I want to finish all. I do not want to come back. This question, you be careful, okay? How many isomers? 4. That 4 isomers, I'll tell you, do I want to draw it? Let's look at it. See, you 4, you can draw this way, okay? It's this one. That's the one. So all is the same side. Okay, what's this? And that's called meso. Now I'm going to draw second one. The second one I'm going to draw is what? I draw this one. And the Cl. And that also is a meso. That's a Q2. Now the third one is what? We draw this way. I'm draw this one. Right. And I'm draw this one. And that is enantiomer. Right. Three color the same side, not chiral. 1, 3 in the same side, 2 in the opposite, not chiral. Now it's 1 opposite, 2 another one. That is chiral, totally 4. Now here is what? Here is a 2 meso compound. Class, I really want you to pay attention. Next year may have a meso compound. So what's the meso compound? Meso compound is pure, number 1. Meso compound have internal symmetrical element, such as the middle of a plane. Meso compound is not chiral overall, but they do have chiral center. Meso compound, superimposable with the middle image. Meso compound, it is optically inactive. Meso compound. You remember. Another one is what? Racemic, enantiomer, diastereomer. Those you should know that, okay? Right. Remember, huh? You not use this one to do the calculation. Do not use this one to do calculation, okay? Because they may have meso compound in the molecule. They may have a symmetry, right? Remember, this 4. This compound compared to previous year is very unique. Now, this one is easy. Did you remember? So what's this? And that one, it is this one is a pyrrole. This one is imidazole. This one is piperidine. This one is pyridine. And you look at what? You look at the p orbital. You look at sp2 orbital. sp2 orbital on the same plane. P orbital is a perpendicular. P orbital is a part of the ring. And that ring is aromatic. So that you 4m plus 2. Now if electron in the sp orbital, just like this one, which is a base, just like this one, That's the base. Now in the p orbital, it's here. It's here. So what's this? It's 3sp orbital, 3sp2, 1, 2, 3. And that p orbital is a part of the ring. You have 2 electrons. So 2, 1, 2, 3, 4, 5, 6. Now what's this? That is not that. This one basically is sp3. You got it? Just said which is weaker is the base is this one. Why? Because it's not a base, it's acid. And that orbital, that pair electrons in the ring, part of the ring, in terms of pKa, let's look at pKa. pKa, this one, P row. That one, P row. This one, it is 11. This one is a 7. This pyridine is a 5.2. Here is a 0. You got it? Okay. This question is common. We discussed so many times. Now the time is good. A little bit stressed out. I wanted to finish. Okay. See, you remember automatic lone pair law. Hydrogen containing heterocycle is a lone pair. It's automatic part of that one. So for P-row, lone pair is what? Is a part of the automatic. It's a part of the ring, not available for protonation, weak base. Pyridine, that lone pair is what? It's not automatic. Basically, it is sp2. So that can protonation, much stronger base. So look at this two, okay? Now that's the next one. See, that one probably you need to remember, okay? So the strength is the automatic amine, emitters of pyridine, and P-row. Here's more nitrogen, not me, it's more basic. That's one. Now look at next one. This one is basically it's a summary. Summary of what? Cyclic, this one. Cyclic, what one? See, it's this one. What's this? Cyclic hexene, solute, carbocation. Plus, why use dark? Why use dark? And use dark is what? Because HBr, if not dark, you have light, so we form radical, okay? Right, so look at one by one. So the mechanism in this one is what? Now, here's a nucleophile. So you form carbocation intermediate, and that reaction we call the electrophilic addition. Right? The second step, so your product, right? That's addition. So through carbocation intermediate. Carbocation intermediate. The choice should be this one. Now the second one is what? That reaction, do you think it is a radical reaction? It is a radical reaction. Why is a radical reaction? See? Radical, right? And now what happened? Now what happened? One electron go to here, one electron go to here, one electron go to here, right? So you get radical, okay? You get radical. You got it? Then you will continue. That's the radical mechanism. It's not carbocation. Now what's this? And you know, halogen, and that one form hydronium, brominium, right? So basically you form this way. Right, for the three-number ring. What's this called? Bromium, not carbocation. Now the second one, you go to here, you broken here. It's anti-stereochemistry, right? Now next one, what's this? UV. You see the UV is what? That one, just the MBS reaction, also is radical, right? UV is radical. Got it? So see here. This one, if you know organic chemistry, it's nothing. This is just a joke. Too easy, right? See, reagent, if this one normal condition, have to carbocation. For this one, you have to radical. For this one, it's what? See, polonium ion, three-number ring. For this one, it's the same. The difference is what? That one repeat, the complete different strength of nucleophile, right? Now for this one, it's what? And that from mercurium ion, then you do the reduction, right? So what is hydroboration is what? No, it's one step, four-number ring transition state. Got it? Okay, let's move on. Yeah, this is so easy. Okay, organic chemistry is so easy. Now look at here. Look at this one. The choice should be this one. Okay, why? Why? And the reason is the reason for SN2 reaction. The first one, you want what? You want or primary or it's a secondary organohalide. That's the first one, which we call the substitute, the substrate. The second one, you want a good leaving group. Like tosylate. The next one, you want the solvent. And that solvent should be polar aprotic solvent, like acetonitrile, like DMSO, right? That's the SN1 reaction, right? You base this one, that's the choice. This is the good, it's a primary carbon, and also it's a good leaving group, right? So here I summary for you for the SN2 reaction, okay? You want a good leaving group, that's a stereohedron. That's a good leaving group, stereohedron, right? Do you see? Yeah, I'll go to next one. Almost done, we are good. Now this is good. This one good. How are I going to approach this question? If I will approach this question, you draw the chair. A chair. Now it doesn't matter, I'm beginning here. So that is done. And that one is done. And this one is down. This one is up. This one is down. And this one is up. So now you count. So it's only one. Oh. So it's only one. What's the question? The question said, how many hydroxy group in the equatorial most stable one? How many? 5. That should be 5. Okay, right? So you look at Olympic learning, see cyclohexane is more equatorial group, more stable. But you remember they will have called the ring flipping. Ring flipping through what? Through the sigma bond notation, sigma bond called conformation. So you are going to convert this one to this one to here. You change what? Change up or down stereochemistry. This is very common. That's a sugar. That's a sugar. Next one, this one is not organic chemistry, but you know what? If you know little biology, it should make sense. This question about what? This question is about protein. It's about the protein Protein what? Protein folding, right? So basically it's what? You have two groups. One is called hydrophobic. And the hydrophobic, that residue should be inside. Now another one, it is called polar and charged residue. So that's called what? That's called hydrophilic. Hydrophilic, which go to what? Go to the water in the surface. You got it. That's basically it's like protein folding. Just like see that hydrophobic go to inside, polar charged go to outside on the surface with water. Now you look at. So what did you see here? And that one is what? It's partly charged pH 7. This is hydrophobic. Now look at this. That become minus, right? Sweet ion. Did you remember? Sweet ion here is plus, here is minus. So, and that is hydrophobic. Right? Now what's this? It makes sense. If not this one, of course it's not this one. It's a good question now. You already eliminated two. That is this one. It's this one. Okay. It's this one. Now what I write here. Let's look at what I write. Amino acid most is buried in the protein internal hydrophobic, including, see, you remember it. Okay, any more here? The common find in proton core, ammonium find the surface is have a charged residue on the surface. Interact with water, often it's what? It's a solvent exposed. pH 7, and charged chain go to the surface. Hydrophobic go to inside. Oh, I think that's it. So this one will go to inside, and that's the discussion. I should more detail, like at the beginning, several questions because of the time. What do you think? I want you feedback. Do you think it's good? I planning many way this, and all individual questions we are going to use a topic to cover. Okay, any question? Okay, I will see you guys on Wednesday. Good night. Bye now.